Wood was probably man's first fuel. He set fire to it, he obtained energy from it, he warmed himself, and he cooked his food. The industrial age opened up new ways of using energy. There was extensive use of other fuels, such as coal and petroleum. And today we're finding many new uses of energy, but scientists are still hard-pressed to develop enough new energy sources to meet all of the demands that they foresee for fuels of the future. Now, our guest was a key figure in discoveries that will lead to the use of vast new energy sources. He was co-discoverer of 9 transuranium elements and scores of radioisotopes. Among these discoveries are plutonium and uranium-233, which will both lead to future exploitation of atomic energy. He's also chancellor of the Berkeley campus of the University of California and Nobel laureate in chemistry. I'm sure I need say no more, for I'm certain that from this description you will have recognized our guest, Dr. Glenn T. Seaborg. Glenn, we're glad to have you back with us.
Well, thank you, Earl. It's a pleasure to be with you again.
Can you tell us how critical this need is for new fuels?
Well, I think, Earl, I can show that best if we'll step over to these charts. These charts depict the relative world population and the use of energy. The height of the figure in 1900, for example, corresponds to the world population in 1900, and the height of the block here, the relative use of fuel at the beginning, you might say, of the technological era. Now, the world population increased about 50% between 1900 and 1950, whereas the use of energy trebled in that same period. And the world population is expected to increase by a little more than 50% between 1950 and the year 2000, but the world use of energy is expected to go up 4 times in that same period.
What are the principal reasons for this increase?
Well, the standard of living of people all over the world depends on their consumption of energy. That's why we have such a high standard of living in the United States, for example. We consume energy per person something like 2 or 3 times the rate of some countries in Europe, and of the order of 10 to 1,000 times the rate at which energy is consumed per person in some of the underdeveloped countries in the world.
Glenn, where are we going to get all of this additional energy that we need?
Well, let's have a look here first at our conventional sources of energy, and then a little later at the possible energy sources of the future. First of all, of course, there's the familiar hydroelectric source of power. This is a stationary source. It develops much of the power that we use and is largely undeveloped, as a matter of fact. We have much more possibilities here. And then we have the fossil fuels, coal, which is used also to develop power and energy in large stationary plants, and petroleum, which is another fossil fuel and which is used to develop electrical power along with coal, as well as more commonly to propel automobiles and give us mobile sources of energy. And they're also prospective sources of chemicals.
Glenn, what can you tell us about the status of the development of the unconventional fuel resources?
Now, if we'll look over here, 2 of the unconventional or future fuel resources depend on the nucleus of the atom. That is, it depends on getting energy from the nucleus as opposed from the rearranging of the electrons in the atom as you do with fossil fuels. The first here already being used is the nuclear fission source, depending on uranium and thorium, and we have a sufficient amount of uranium and thorium on Earth to enable us to have this energy last for hundreds of years, this source of energy. Now, the second is also a nuclear source, but this is an undeveloped source which depends on the light nuclei of hydrogen, the thermonuclear source, and this is the fusion source and is the energy of the future if we can solve certain problems. And then we have the potential solar source, a tremendous source of energy, but a source that will only be obtained after we've solved a great many problems. Now, to tell us more about these new sources of energy, Earl, I'd like to introduce Dr. Tom Pigford, who is the chairman of our new young department of nuclear engineering at the University of California. Dr. Pigford has had a great deal to do with the design of nuclear reactors. And I might say, incidentally, that this new field of nuclear engineering is one that young people who are interested in going into the applied aspects of science might very well take up.
Thank you, Dr. Seaborg. Tom, can you tell us how you get the energy out of the atom?
Yes, well, as Dr. Seaborg had mentioned, there are two basic processes. I call them burning water and burning rock. I'll talk about burning water later, but burning rock is fission. We get uranium from rocks, and so we are fissioning the uranium. Now, I'm sure that the mechanism of fission has been described many times, but I'm going to go over it very briefly first. Here we have a heavy nucleus, like uranium-235 or plutonium or uranium-233 that one might get from thorium. And here's a neutron coming along, hitting that nucleus and splitting it into two parts.
Whoop, we just lost it.
Which releases a lot of energy, and it also releases a few more neutrons which go along. Now, these neutrons are very important because they can go along and hit other uranium nuclei and cause fission, and they propagate the chain reaction.
Yes.
Now, one trouble, though, is that these neutrons are moving at very high speeds, and they don't hit nuclei very easily when they're going fast. So we have to slow them down, and that's the trick. And in a practical reactor, one does this by using clumps of uranium and separating those clumps by neutron slowing material, such as graphite.
Now, that's what you have in the unit that you brought to the studio here.
Yes, this is one of our experimental reactors, which is indeed a graphite uranium reactor.
We'll have a chance to see more of that a little bit later. I wanted to ask you about the complexity and how much this costs, and is it ever going to get to the point where it will be less expensive than other methods of getting energy? When I look at all of this very complicated chart here telling what happens, I'm a bit confused.
Well, therein lies one of the problems of getting economical nuclear power from fission. Here's the process we really want to occur. There's a reactor, a turbine generator, and there's electrical distribution system. But to put this into operation, we must have a large uranium mining industry, a milling and purification industry. We must have a process that purifies the uranium fuel elements that come from the reactor, large isotope separation plants, waste disposal for the fission products. And all of these have a bearing upon the economics. But I must say that there are important differences. The regular plant has large amounts of coal that go into it. And therein lies one of the key, because it requires a lot of transportation, these conventional fuels, and that affects the economics greatly.
We do have plants of this kind in this country in operation at the present time.
Yes, and nuclear plants, a very large industrial-sized plant, went into operation this year near Chicago. The Dresden plant, which was built by General Electric in this area, and also Bechtel Corporation. The Pacific Gas and Electric Company has a plant.
Well, the Valicitos.
The Valicitos plant. It's an experimental plant that's at General Electric's laboratory. I believe we have a movie here of some of the Valicitos equipment and experiments. This is a picture of a fuel cask, we call it, a way that an experimental fuel element which has come from the reactor is taken behind heavy lead shielding into the laboratory for examination. There we see some mechanical fingers pulling it out of the cask. I might mention that the Pacific Gas and Electric Company does plan on building larger plants. They have one which will shortly go into construction near Eureka that will be 30,000 kilowatts, and in 1965 a 300,000 kilowatt plant. They hope to break the economic barrier then. Here we see the mechanical hands taking the fuel capsule out, and he's going to dump, there it is, uranium dioxide. Those black pellets are the fuel material. And now we see a new fuel element being loaded into the core of the Valicitos reactor.
How often do you have to change these fuel elements?
In a regular nuclear power plant, once every 2 or 3 years perhaps. In this plant, which is experimental, they change them more often to examine the experiments. Now,
the various things that we've talked about, Tom, let me go back a minute by way of review. Let's see, we talked about burning coal, we talked about burning oil, and of course you burn rock during fission, but let's get this glass of water over here again, because I think this is very, very important. At least it was quite interesting to me, the fact that you can get energy out of this water in a way that we haven't as yet accomplished.
Yes, burning water is the process that intrigues us all. First, it's one of the largest energy sources. It's almost impossible to comprehend how vast it is. The actual energy comes by extracting heavy hydrogen, which is present in the water. Not very much of it, but there's enough of it there to make a lot of energy.
Yes.
For example, in this glass of water, there's enough heavy hydrogen to generate as much energy as 30 pounds of coal.
That much from this glass?
Yes. And the water and the heavy hydrogen in the oceans of the world will last us for 10 billion years at our present rate of consumption.
How do we get the heavy hydrogen, and once we have it, how do we use it?
Well, it's not difficult to extract. In fact, it's being extracted commercially now, and it's really quite inexpensive for this process. Using it, though, is another matter. Now, let me illustrate there. Heavy hydrogen is a particular isotope of hydrogen. It has a proton and a neutron. We take two such nuclei and bring them together. They fuse like that, and they end up by forming a heavier nucleus. This happens to be helium-3. It has two protons and one neutron, and an extra neutron. It releases a lot of energy, and that is the reaction that occurs.
Now, earlier, you were sketching for me over here one of the suggestions by how the method by which this could be handled. Could you go into that again, Tom?
Yes.
And see how this works.
This is, in fact, a much more difficult reaction to carry out than the fission reaction. You're trying to bring two charged particles closer together so they can react, and the charges repel each other. Well, you could accelerate them, but you get less energy out than you put in.
Yes.
Another way is to heat them to high temperatures, and then they hit each other and react. That's the way the sun works, as a matter of fact. But we need temperatures of 100 million degrees, perhaps.
Well, that
higher.
much.
And therein lies one of the problems. How do we keep the heavy hydrogen gas together, and what sort of containers do we use? Well, this is one of the ideas. One maybe has a large tube containing heavy hydrogen gas, and you can heat it up start the reaction by putting a spark discharge across it. And the discharge heats the heavy hydrogen. It will hopefully react and create a lot more energy. And the process of electrical current going through the heavy hydrogen generates a magnetic field, which tends to go around the gas like a corset. And it tends to compress the gas, keeping it away from the walls of the container and holding it together. It gets very hot. And that's the magnetic bottle effect. That is the principle of practically all the ideas to carry out practical fusion reactions.
That's what this demonstration does.
Yes, we wanted to demonstrate just how powerful these magnetic compression effects are. And I'm going to turn on the high voltage source first, and you will see that we are going to charge up to about 10,000 volts in this experiment. Now here we have an aluminum tube. The aluminum is analogous to the heavy hydrogen gas in this experiment. I'm going to put it into this plastic tube, and surrounding that you see this coil of wire. This is a magnetic coil, and as the high voltage discharges through that coil, it generates a powerful magnetic field compressing the aluminum. Let's see what happens. And besides making a lot of noise,
that really popped.
It has really compressed that aluminum, and there is the reacting heavy hydrogen, which is kept together and kept away from the walls.
Now, my next question then is, I see how it works here on the demonstration, but have you as yet been able to operate a thermonuclear reaction by this technique?
Well, there's been a lot of research on it and some very promising progress. But also the researchers have found that it's a much more difficult operation than they originally thought. And we feel that it will be a long, long while before you will see working thermonuclear reactors, especially practical ones.
But it is coming.
It is certainly coming, and it must come someday.
Tom, one of the items we mentioned a little bit earlier was the use of solar energy, and I can remember as a youngster that on the outside of the house we had one of these big heating units which heated the water for the kitchen. This is practical and has future applications.
Yes, as Dr. Seaborg mentioned, there's a great deal of energy coming from the sun. In fact, coming every year from the sun is far more energy than we generate. But it's difficult to use on a large scale. Indeed, there are some houses which are built for to trap the sun's rays for heating, but that's a small portion of the energy required that was mentioned earlier.
Yes.
Here is a demonstration to illustrate the problems of utilizing the sun's energy. We have here a bank of sun lamps, which represents the sun, and in this bucket we have a copper coil. The coil is fed by water, and it's black, so it will absorb the energy. It's put down in this bucket, which is lined with aluminum foil, and so the bucket traps the rays and bounces them around, and many of them are finally absorbed in the coil, heating the water. And the water forms steam, and you see is driving a tiny turbine here.
Right.
Now that is basically the way most of the solar energy conversion processes work. Heating your homes, which will be the main process, or perhaps someday, but a long way off, a large power plant.
You know, many times in the past we have had diagrams of how reactors work. We've done everything possible without actually having a reactor. And for the first time in 11 years on Science in Action, we have a real reactor here in the studio, and I'm quite eager to find out just how all of these things work. Could you tell us about it?
Yes. First, I want to give you these radiation monitors just to ensure the safety of operation here.
It is perfectly safe for us to stand this close to the unit.
Oh yes, this is quite a safe experiment. Our students work with this almost every day at our campus in Berkeley. Now this is the reactor. Really, it's a small portion of a reactor. We call it an experimental pile. It's a copy, as a matter of fact, of the very first reactor that was built in 1942. It's a sort of a Model T of the atomic age. But it's good for training, and it's good for research. We can do some good research with it. That's uranium metal.
It's safe to handle?
It's quite safe to handle because it hasn't reacted very much and doesn't have very much radioactivity in it. And between the chunks of uranium metal, we have blocks of graphite. That's what slows down the neutrons, you see, and they bounce out of the uranium, wander around in the graphite, and hit other uranium and cause fission. Now this particular one is far too small to be a critical chain reactor. Too many neutrons are lost by leakage. We would have to make it about 300 times as large to make it critical. But we can demonstrate this one because we brought along an artificial neutron source.
I noticed this was paraffin that you had inside of the barrel here.
Yes, that's for safe shipping of the source. And the neutron source itself is contained in that small metal capsule at the end of this wooden stick. I'm going to put it in this hole in the reactor, and let's see what happens. We can observe by the count rate and the flashing lights and the clicks that something is happening. And the neutrons from this source are in fact wandering around in the graphite, causing fissions, giving rise to more neutrons, and that causes the higher radioactivity that you see on this counter. Perhaps you noticed also the increased flicking from
down here at a very fast rate. Well, now then, with this kind of a unit, you could generate steam, and then you could get electricity, do anything that you wished with it.
Yes, we would, in this case, pass water over the hot uranium rods if it running as a reactor, and the hot water would then generate steam. I might mention that for a power plant, we would have to have 8 to 10 feet of concrete between us and the reactor because of its lethal radiations.
Suppose I came into you and I said, I want one of these in my industrial plant, but I need some people who know how to operate it. Could you provide those people?
Yes, the University at Berkeley, as well as many other universities, Stanford in this area, are training students in nuclear engineering, by and large at the graduate level. It's a very active program, a very interesting one. We just turned out our first 2 PhD men this spring.
Oh, good. Now, Tom, I'd like to go back right now and ask a question of Dr. Seaborg, which has to do with what we've seen happening here in the past. In other words, this kind of equipment will now do some of the things that oil and coal have done. What is the future now?
Well, these won't replace oil and coal right away. We have a supply of oil and coal that will last for decades. They develop power economically and very efficiently. However, in time, these will supplant them. We should begin to think about using our oil and coal eventually as sources of chemicals, and they're really irreplaceable for this purpose. And then, as we need to have more and more energy throughout the world in order to increase the standard of living of the underdeveloped countries, this source will become important. And this is important because we need to increase the standard of living of these people so that they can increase their educational possibilities, which in turn should lead to better understanding among people and contribute to world peace.
Dr. Seaborg, I want to thank you, sir, once again for being with us on Science in Action.
Pleasure.
And Dr. Pigford, our thanks to you, sir, for these very fine demonstrations. Thank you. Jay Jacobus is waiting for us on the other side of the studio. Let's just step over and join him. For our Animal of the Week, we go to Midway Island in the Central Pacific, the breeding ground of the albatross. Now, Ted Mundorf is here, and he knows about the albatross, having studied them. Ted, will you tell us some of your observations on this remarkable bird?
Yes, sir, we do have a remarkable bird. Here we have the white or Laysan albatross. It is the most popular of the two species that are found at Midway. It actually inhabits the inland portions of the island and is the most pleasurable to watch. They're very fun, actually.
Yes.
Here we have the black. It inhabits the outer portions of the island away from human habitation.
Oh, what's going on here?
Well, this is the characteristic Goonie bird dance. This is actually prior to mating, during, and following.
That's fantastic. Look at that.
Yes, they keep this up. This is quite a sight to behold.
Well, three of them now.
Well, sometimes the third bird does interfere. He wants to get in the act, I think.
Bouncing up and down all over the place. And these are large birds, too. What is the wing spread? Something around 8 feet or so.
8 feet up, actually 14.
Let's see, how many eggs there? I can't make
One.
that. Oh,
One
one
egg,
egg.
Earl.
And the nest itself seems to be sort of built up from the ground.
Yes, it's a conical-shaped pyramid. Here we have the young bird. He will keep this down for 6 or 7 months.
And during this time, I guess he has to be fed by the parents.
All this time, he eats regurgitated food, as you see right here, and by his own parents.
Parents always know their own youngsters.
Yes, and the young chick stays by its own nest. Here he's losing his down. And about this point, they begin to flap their wings and try them out for size.
He has
Here
to
we
run
go.
to take off, doesn't he?
Yes, a long run is required.
Amazing bird. Ted Mundorf, I thank sir for coming to Science in Action to tell us about the albatross.
Nice seeing you, Earl.
We hope you've enjoyed our program this evening. We'll look forward to seeing you 1 week from this time. Thank you very much.